he will make a talk about the cybersecurity. Yes, please.
Okay, so I assume you can see my screen now.
Yes.
Yes. So, hello everybody. My name is Nikolaos Doukas. I'm an associate professor in the Hellenic Army Academy. This work it should have actually been presented by one of our MSc students, but due to some superior problems, it couldn't be done, so I will present it. The title of the work is Content-Based Image Retrieval Using Deep Learning Techniques. So we'll see a brief statement of the problem that we are facing, the methodologies and the data sets that we used, some comparative analysis of the results that we have, and the plans for future work. Pardon?
Professor Markovsky, please turn off your... yes. Professor Markovsky, please turn off your... Let me see if I can do it.
Never mind. Okay.
Yes.
So this is relatively recently started research. So we are presenting here the first results that are preliminary, but we that are of interest. Maybe by the submission of the final analysis, we will have some extra results. To show. So let me not waste any more time. So content-based image retrieval systems are essential for various fields of for various applications and fields like this digital asset management and multimedia searches. Searching based on images is much more intuitive for users. So again, in this field, this research can contribute. It enables users to find the relevant images very quickly and improves the experience and the operational efficiency because they have something in mind, an image in mind. They can search with that image, or it's easy to classify images into categories, so identify items of interest within a scene very fast. Traditional content-based image retrieval methods rely on handcrafted features, so the well-known to most people that have tried anything in the field of recognition, task of trying to pick up the necessary features that will do the optimal or as good as possible recognition without expanding the parameter space too much. Content-based image retrieval is a technique that uses image content rather than metadata to search and retrieve images from a database as well. So the aim is to identify images that are visually similar to a query image based on content features, which is a problem that can be expanded to image classification. So given a huge and diverse data set of images, classify them into categories, classes, subclasses, based on some necessity for the application. And for this reason, a technique from machine learning called feature hashing is which is a fast and space-efficient way of vectorizing features, which means turning arbitrary features into indices in a vector matrix, is used and is seen to provide good results. it applies a hash function to the features and using the hash values as indices directly or after a modular operation rather than looking up indices in an associative array. In addition, feature hashing can be used for dimensionality reduction. So as I said, instead of trying to select the features that are necessary for the discrimination that is required, to use some kind of learning technique in order to achieve all that. Also, the hashing function is also something that is produced after learning. Sorry, this is a repetition. So let's go to the traditional image descriptors. These are manually engineered and failed or become too cumbersome to use in the case of complex semantics or visual data. They perform poorly when images contain variations in lighting, in occlusions, complex structures, scaling, transformations, and lead to reduced retrieval accuracy. Also, conventional retrieval methods such as linear search and exhaustive comparison become computationally too expensive and impractical, especially since the size of image databases that we are faced with currently is ever increasing and already is beyond the limits of such approaches. And techniques that are based on dimensionality reduction or simple feature matching are unable to maintain high retrieval accuracy for large scale applications. So there is the need for methods that can simultaneously improve retrieval precision and reduce the computational cost, especially as datasets grow exponentially, essentially these days. Scalable solutions should ideally efficiently map high-dimensional image features into compact representations that enable real-time image search, even in large-scale data sets. Also, one of the problems that we're trying to address in this research is explore state-of-the-art deep learning techniques that can automatically learn the effective image representation for retrieval. So essentially, by learning, design what we call the hash function in the previous slide. So the aim here is to implement hashing-based methods that convert high-dimensional features into compact binary codes for fast similarity search. Do some systematic comparison of different models and different classifiers that so as to identify methods that are suitable for our needs. And looking further away in the future of this research is to apply the same principles that seem to have high potentials to other applications, such as intrusion detection, digital signature, and arbitrary data classification, not just image data classification. Now, just to clarify a little bit more the difference between hashing as we know it from cryptography and this hashing here. So instead of using handcrafted features that are picked by hand, deep hash methods are used that you employ convolutional neural networks to learn features automatically after the training period. Traditional methods use a two-stage optimization, while in the case of deep learning methods, the training goes end-to-end, essentially with, of course, the epochs that are used in the training, but there is no further interaction in that. And deep hashing methods seem, as we will see in the results, as we have seen, we won't see these results today, outperform traditional hashing in both in terms of retrieval accuracy, speed, and large-scale data sets. So if we give in a tabular form the comparison between the two approaches, in terms of feature expansion, we have, instead of hand-picked features, neural networks that learn features from raw images, which is also very important. The fact that even there is no need even to extract features from the images and then try to select out of the classically known features of images which ones are should best be used. The optimization, the feature extraction in traditional methods is separated from the hashing part, while here with a learning technique, with a learning approach, there's a joint optimization of feature learning and hash code generation. Semantic representation, there is limited semantic understanding, and so the hashing, the normal traditional hashing methods are focusing on individual and specific features, while the deep hashing methods can capture high-level semantic information and result in more accurate retrieval and more generalization. The scalability, of course, here there is very little comparison because traditional hashing will struggle in large-scale datasets due to high dimensionality of features, given the fact that we're trying to use raw images, especially. And while deep hashing is efficient and scalable for large datasets, and by producing compact binary codes, the accuracy is lower in traditional methods due to the disjoint learning process, while the alignment between the image features and the hash codes produces better accuracy in the deep hashing. And of course, the speed is slower both in training and retrieval phases, while deep hashing, even though it might have some demanding training phase, will in general produce faster retrieval via the optimized binary codes. So if we try to look at the methodologies, there are 5 different methodologies that have been examined, and we'll share a few words about each one of those. So first one is deep supervised discrete hashing. So this aims to learn compact binary codes that effectively capture the semantic similarity between images. It could be images of the same semantic entity, but highly diverse visually. Imagine how many different flowers or how many different animals, how many different cars could be seen. But this aims to learn via these compact binary codes the similarity. It uses convolutional neural networks to extract high-level image features that are aligned to semantic content, and use a joint function that combines two main objectives: the classification loss, which looks at how discriminative the binary codes are, and the pairwise similarity loss, which looks at the similarity, preserving the similarity between images that should be considered similar. The method achieves high-level retrieval accuracy and computational efficiency, and demonstrates good performance on various benchmark datasets. Sorry for this. The main object, and so we go to the next method now. Deep supervised hashing is to learn compact binary codes that accurately preserve, again, the similarity between images. The method uses supervised learning to encode pairwise information, information into binary hash codes, ensure that similar images map to codes that are close in Hamming space. It introduces a custom loss function that combines a discriminative term and a regularization term. So the discriminative term ensures that binary codes for similar images are close and dissimilar images are far apart. And regularization helps the network approximate binary values effectively. It is then using pairs of images as input, where as the pair is labeled as either similar or dissimilar. So the labeling of the input data is slightly different here. It achieves high retrieval accuracy and computational efficiency, and demonstrates superior performance of various, again, on various data sets. The deep hashing network has the innovation that it has the ability to optimize both feature extraction and binary codes quantization with a single deep network. Unlike other approaches, it reduces the quantization errors and ensures that the length binary codes are tightly coupled with image features. It uses a Bayesian framework to estimate the optimal hash codes during the training. And again, it has two loss functions: the pairwise cross-entropy loss that preserves semantic similarity by encouraging the hash code of similar pairs to be close and dissimilar pairs to be distant in the Hamming space, and minimizes the discrepancy between continuous and discrete versions of the hash code, so that final codes are near binary values. We're going to the deep pairwise supervised hashing that integrates, again, both feature learning and hash code generation. So it allows for simultaneous optimization of image features as binary codes, ensuring better compatibility between the image features and the binary codes. It employs a pairwise label information approach to directly optimize for image similarity, and uses, again, pairs of images as training samples. Also employs convolutional neural networks to learn features directly from raw image data, so eliminates the discrepancy between pre-extracted features, and allows DPSH to outperform other hashing methods in both precision and efficiency, making a strong candidate for large-scale image retrieval scenarios. Having had a short overview of the data sets, of the techniques, We use two data sets that are very widely used, so they're good for benchmarking. Cypher'10 and Cypher'100. Cypher'10 consists of 60,000 color images divided into 10 classes. Each image is 32 by 32 pixels, includes everyday objects, for example, airplanes, cars, birds, cats, and more. And it was divided in 50,000 training images and 10,000 test images. The Cypher'100 is a more complex data set containing 60,000 color images again, but this time divided into 100 classes. Each image has 32 by 32 pixels. It has a broader range of categories, making it more challenging, and again, is split in the same way. One observation here, the size of the images is relatively small, 32 by 32, which means a limited number of features. And this is important for the targets that we have set for the continuation of this research to use small samples for the classification, small size samples for the classification. For the execution platform, Google Colab was used, mainly due to the computational power required. All these techniques that we've described are quite computationally intensive. In a normal personal computers would take in the order of days to be executed. With Colab, things become a little bit easier in terms of processing speed. Of course, trying to optimize the implementation so that they do not require extreme resources is also part of this research. So the hardware utilized was using NVIDIA Tesla KIT T4 GPU that is available in Colab, up to 35 gigabytes of memory, and okay, this space 235 gigabytes, but that is not something really extreme. In terms of languages, these are Python implementations that are using, of course, deep learning libraries as much as possible, but being Python may be a little room for optimization and implementation in other languages may be opening up for the future. So Python version 3.10.12 and compatible PyTorch, NumPy, and SciPy versions for numerical operations. And all these were done using Jupyter notebooks that are directly supported in Colab and allow integration, visualization, experimentation, and collaboration in these early stages of the research. So the Colab runtime environment was configured to use the GPU. So in this table, we see the results. The results are average success rates based on a relatively small number of runs of the order of 10, due to mainly that it's quite demanding in terms of processing time still, and also, of course, these are the first phases, and they are compared to reported results from current literature in a similar methodologies. So in most of the cases, sorry, there are some differences that we'll discuss a little bit further how they can be justified from what is reported in literature. We can see that the success rate is quite high, is significant. The experimentally achieved one is slightly better than what is reported in most of the cases, except for one case which is slightly worse, and one case which is quite similar. And one observation that we will also talk about in the next slide, that the HTPH method was able to be tested on the more demanding data sets. It had good performance in the more demanding data sets, and this is something to be considered for the future research. So the HTPH algorithm has been tested in a more complex problem. As we said, the Cypher 100 dataset has got more classes, and given that the number of images is the same, so the problem becomes more difficult both in terms of training, the less samples on which to train each class. As I said in the table that we saw before, there are observed differences in the precision and retrieval accuracy when compared to results reported in research in the original papers with first presented these techniques. So potential sources of the difference are the selection of the number of training epochs for better results. We have observed, without having a statistically significant conclusion yet, that maybe sometimes the training epochs could be stopped earlier and achieve better results. The hyperparameter settings, so slight variation in learning rates, batch sizes, and optimization strategies could impact the model performance, and this is something also that current research is looking at in order to optimize. Difference in data preprocessing, so in normalization and augmentation strategies. And also, given that in each run, the selection of the training and the test images was a bit random, there may be room for employing some smart technique in order to select the diverse images for each class so that the discriminative ability is increased. So in terms of future work, given the conclusion and in terms of conclusion and future work, one important conclusion is that HTPH model was shown to be more capable of discrimination in larger and more complicated data sets. From the remaining models, DSH, DSN, and DBSH have demonstrated better performance than the SDH, even though this was not reported in literature. So the future aims are to evaluate these models on larger and more complex data sets, and expanding experimental evaluation to include more challenging for better understanding of the scalability and robustness of the models, and prefer comprehensive comparative analysis to analyze these differences in performance. The potential causes for the variations in the results will need to be quantified more in order to draw conclusions and produce a better system, and also for training conditions that are expected to lead to better ability to generalize. Also investigate alternative techniques for classification, attribute selection, and hyperparameter tuning for dimensionality reduction, employing techniques such as a random forest and grid and random search that have been seen in other cases to be beneficial in this direction. Going a bit further into the future plans, the idea is to apply to different data like network traffic and program behavior in order to include in other kinds of systems like intrusive detection systems. Also to raw binary data, so it's indifferent if it's an image or any other kind of binary data. And also to further, the ultimate goal is to be able to design customized loss and pairwise similarity loss functions that can serve other purposes. Here, they were chosen to serve the purpose of similarity, but in some cases, like in some cryptography cases, for example, or digital signature, we could be looking for enhancing, amplifying dissimilarity. So thank you for your attention. Open for any questions. Here you see the emails of Kyriakos Stefanidis, who, as I said, is the master student working on this research, and myself.
Thank you very much, Professor Doukas, for your presentation and for the short time that you make it. Thank you. Any questions, please? So, Professor Doukas, we saw that you're using hash functions on that system that you propose.
Mm-hmm.
Yeah, can you explain us how you're using it, in which side of security that you use these hash functions?
As I said, sorry, I stopped accidentally the slideshow. I need to share probably again. Okay. Sorry. So, due to the research here is not into a cybersecurity direct problem, because it's considered with image classification. Of course, it can be used in applications like surveillance or object recognition for fast recognition in a complicated scene of objects of interest. In its mechanism, it is using the hash functions by learning them, essentially. So the learning process is essentially designing the hash functions that can then quickly classify images. So the same principle of the hash functions is served here, but with a different context. So we're currently studying this in order to be able then to transfer this these hash functions, the learned hash functions, into other applications as well.
Thank you very much. Thank you. I got it now. Thank you. Thank you. So because this was the last one of our presentation, of our session, thank you very much, everybody. And we'll have a small break now, and we will come back with the other sessions. So thank you very much. Have a good day.
Bye.